Hey, everybody, welcome out to the AI Think Tank podcast. For our 11th show, we're going to be talking with Bhupinder Bhullar from SwissVault in Switzerland. And SwissVault is pioneering data storage in ways that made me really excited when I first learned about them. And this is actually their second time on my show. The first time it was completely private, it was for MIT cohorts. Probably about half a year ago, and to rave reviews. And because we know we're going to need a place to put our data, working with AI and of course, all the big data we're having to crunch as scientists as well. So it's a pleasure to have you guys on. And there's so much innovation that you're involved in. I'm going to kind of let you take the lead on this, Bhupinder. How are you doing?
I'm very good, thanks, Dan. Wonderful to be here again.
Uh-huh.
Really, thank you and the AI Think Tank for sponsoring us for this presentation.
Absolutely. Yeah. It's great. It's exciting because we work together in different areas, away from what, we have different projects together. So, and different
Yep.
associations. So it's really exciting. And I see, what is it? New Jersey Big Data Alliance, uh, out here today too, different people representing a lot of major positive impact on the East Coast for data management and what's really become an industry-wide problem. For lots of reasons, be they economics or environmental, and just space and less waste. We're looking at a lot of gains in using something that could really minimize those costs and needs, and that's one of the things that SwissVault does. You guys really surprised me with your high performance demos and what you're able to do. And as a digital forensic specialist, as someone who's worked with devices and hardware for over 20 years now, it excited me. And as a Linux user and Unix user and someone who builds from scratch, I thought to myself, wow, that's a lot of power. That's a lot of performance. And I thought it was about a third less space being used for some of these things. So I don't want to
So,
put some raw numbers out there. Okay. But it was phenomenal and exciting. So tell us about what is really the Vault file system and your entire approach to managing this huge concern that we all have right now.
okay, should I start with the slides?
Yeah, you know what? The visuals really helped me the first time around. I think they'd probably help
Okay,
everybody else. So
okay,
let's
perfect.
take
Then
a
I'll
look.
just start. I'll share and I'll start the presentation then.
Absolutely. All
Okay,
right.
well, thank you very much.
Thank you.
So we are delighted to speak, and especially about our presentation about on what Dan just alluded to, is that we're increasing the efficiency of data, especially for this AI ML age. And Dan had suggested we put definitely the sustainability part,
Hmm.
and we are really proud of the fact that we can push data to be more sustainable in data management. And I'll start with just one little fact that you may not be aware of, and that is that when you send one email with one attachment, it has the same carbon emissions as one small plastic bag, the production of one small plastic bag. And we send millions of emails per second, per minute, and it'd be unthinkable if we threw out millions of plastic bags per minute as well. And so data's carbon footprint is due to the intense energy and infrastructure demands. And so basically, right now, today, the numbers are that 4% of the global energy production, that is the entire production of coal burning, so hydroelectric dams, solar panels, or nuclear power, all the energy that's produced, 4% of it goes towards just to our data needs, just data management needs, the transmission of it, storage, and compute. And 2% of the global carbon emissions, that's produced just by data. That's more than what the airline industry or the automobile industry produces. So it has a massive carbon footprint and a massive energy draw. And that's concerning a lot of industry leaders, because if you look across the sectors, there's many cities are putting a moratorium on data center development because they just can't manage this infrastructure. And this theme comes back again and again and again. So we're trying to push for that sustainability part. And I'll be delighted to tell you more about it. By the way, just in the preparation of this talk, I was looking for how much energy does Chat GPT use, for instance. And a startling number was that just in the training of Chat GPT-3, before it was released, it consumed 1,200 megawatts of electricity and contributed 550 tons of carbon dioxide. And so just to put that in perspective, that would be what 100 or 120 homes in the US would consume for an entire year. So just for the training of this algorithm, it consumed that much electricity. So what SwissVault does is we're very focused on long-term sustainable data storage. And this is important for AI because you need data, you need to be able to manage that data efficiently. And the more importantly is that you need to be able to feed the data into the training algorithm sufficiently as well. So you need high speeds. So we want to increase not only the efficiency of the storage, but also the performance of the data. And of course, as I mentioned to you, we want to reduce the energy and its environmental footprint. That's the only defensible thing you can do in terms of long-term data management, is basically reducing the carbon, the energy footprint, and the footprint on the infrastructure demands. Because otherwise, we'll never be able to scale and keep up. And of course, what we want to be able to do, and our positioning in the market is long-term data storage. So we say, let's help organizations store data for 100 years. But and we can discuss that as we go. Across all the industry sectors, and the reason why we are here as well is that we see a desire to adopt AI and ML. And it's really adopt now or you will be left behind. So for most organizations, though, the adoption is not that simple. And the reason is because, and this was highlighted by MIT Technology Review Insight article, that many organizations are experiencing growing pains. I mean, if they have data that's growing, you got to put it somewhere. You got to put it on disks or servers. So it's got to go somewhere. And it's difficult to add this equipment and scale up and data migrate, fix bit rot, and fix data corruptions, data file corruptions. So it's very difficult to manage. And this is why many are opting to go to the cloud. So somebody else manages some parts of that headache. But that may not be entirely the best solution, of course, because you give up on things like cost increase, and also the latency also increases as well. So you don't get the fast processing that sometimes is required at the edge, for instance, where data has been created or is required, like hospitals. So, and of course, one of the problems is that also with the legacy equipment is that data speeds are very slow. So that also impacts machine learning and AI because those processing is also slow and inefficient. I think AWS once cited that 100 millisecond latencies cost thousands of dollars in this equation. And as mentioned earlier, there's a high infrastructure intensity that's required to run these operations. Lots of servers, lots of electricity, lots of cooling, and this is unsustainable. So most organizations are facing the moratorium problems from where data center constructions are halted because of the energy demands. And of course, there's also some mounting piles of electronic waste. Every 3 to 4 years, 2 to 5 years, there's a refresh of this electronic equipment that's costing more and more. And what SwissVault does is that we simplify that data management from the get-go. So make it easy for organizations to manage large volumes of data, scale up, fix bit rot, fix file corruptions. And we increase the speeds of the data as well. Using even low performance equipment, we get higher speeds, and so we can reduce that latency on premises or even in the cloud or hybrid approaches. And finally, we focus on reducing that energy consumption and increase the functional life of disk and servers so that we reduce that infrastructure demands. We may, and what we're proposing with our systems is that, which I'll show you, and I'm delighted to show you, is that we're pushing systems towards the edge or even into repurposing old buildings so you don't have to do massive construction. So let's take a look at the framing of the problem first now. And this is what you see on the left-hand side is the converged storage rack. And a fun fact is that the form factor of these server racks actually goes back to like 1880s when Morse code was first introduced, and you needed, along these railway lines, you needed to have the Morse code equipment, and they needed a server, or they needed a rack to hold all the wiring and the connections. And as the telecom industry started with Alexander Graham Bell, the same rack form factor or the same server rack was designed or used or employed for the telecom industry. And as the data storage industry started back in the 60s, then that was designed or incorporated into the data center design. So we're in an industry that's beset by standards that have been adopted for more than 100 years almost. But today, these servers use 50,000 to 100,000 watts of power. And they're very large. They weigh 800 kilograms. I was at supercomputing last year at Denver, where NVIDIA announced their 120,000 watt powers, and they're massive in design that they announced, and they are actually very excited about rolling out. And of course, they produce a lot of noise and vibration, these high maintenance requirements. The NVIDIA designs needed massive water cooling just to keep the performance at a temperature that is tolerable. And absolutely, when you're pushing them through this amount of a system, putting this much data, reliability of data, there's often a 3 to 5 year refresh cycle for this equipment. So that because there's a probability of failure, and because there's a failure problem, there's a loss of data probability. And so those organizations then basically replace these systems just to manage or maintain the data integrity. And there's, of course, a high cost of ownership. So what I'm going to talk about, and hopefully I cover all of this space, is how we reduce that energy consumption by designing new systems, new hardware that can be innovative, reducing that size, weight, and noise. And so maintenance requirements are actually are reduced and simplified, and increase that lifespan from 3 to 5 years to basically maybe 8 or 10 years, so that organizations can get more utility out of their hardware, and of course reduce the overall cost. So I look forward to in the question Q&A to answer any questions around this. And the second part of the framing is that I want to talk about is that in the industry, there are multiple ways where data is being managed. There's also very fast processes that are often memory, but the type of data that we're going to talk about for AI and ML goes toward the base of this pyramid, where you're using tape archives just to manage large volumes of data for long term. And IBM is the leader in tape archives, but if data is in tape archives, it has to be fed into the machine learning apparatus, and that is usually the bottleneck. And of course, there's disk archives as well. And what we're focusing on is, as I said, the base of this pyramid to make it more efficient to store data, manage the data for long term, and basically increase the speeds. And let's talk about it. So let's see how we do that. So we have two solutions. We have a solution for software, and we have a solution for hardware. And I'm going to talk about both of them, but I'm going to talk about the hardware first. The hardware reduces that space and energy consumption physically by redesign of the server rack. And we make it easy to maintain for long-term data archiving, reduce setup costs and operation costs. So here's the typical rack server that goes into the servers. And the server rack has 48 disks on the front. It has fans and the power supply and the compute elements in the back. It's about 57 liters of volume. So we have done a redesign of this server by incorporating our own innovation in printed circuit board technology, and also design form factors and unique parts to reduce that volume down to 7 liters. It has the same capacity of storage, but everything that's on the back here is basically on the compute, and the fans and power is basically on the back of the green board. So we have reduced also by using unique components, we reduced the energy consumption from 1500 watts down to 120 watts. That's a 10-fold reduction in energy, and of course, an 8-fold reduction in size. And that basically, if you can imagine the tower unit there on the left-hand side, is about the size of a very large loaf of bread, basically. And but it has a significant amount of storage in a small volume. And we can use that to build very large systems. So what I show you here on the left-hand side is the standard rack that would use 5 terabytes using 5 terabytes of disks, would have 2.5 petabytes of storage in this converged form factor, compute and storage. In our system, which is compute and storage as well, would have 10 petabytes of storage. This is what we are developing to show. And the volume is 2.57 meters cubed, whereas ours is 0.74. This is 1/3 the size, but 4 times the storage. So the density of data storage is now surpassing Moore's law and allowing us to store more data in less space, just by physical redesigns. And the energy consumption, 7,200 watts per petabyte in the converge rack versus 780 watts per petabyte, a 10-fold energy efficiency just to manage large volumes of data. And there's significant compute and storage in the storage form factor, 128 CPUs and GPUs, and we're enabling them to use more. We're looking at the second part of the equation, which is energy efficient computation. And as I mentioned to you earlier, when you have data centers, it's a high concentration of infrastructure, and it makes it almost difficult for getting new construction being built by urban centers because they can't meet the energy demands. And that's why these large servers like the converged rack are basically very difficult to manage at the edge. And what we want to do is we want to push systems towards the edge where data is being created and data is being consumed, or data is being computed as well. And so what you see on the red circle is a design by an organization that's building 5 petabytes, 150 kilowatts of energy. And in the green circle, you see our design, which is 5 petabytes using 5 kilowatts. We're pushing this towards the edge where we can store more data in basically office buildings or in by cell phone towers or in anywhere in urban centers where data is being consumed. Okay, so I'm going to transition now to the software because it's a critical component of our solution. But unlike our hardware, the software can run on any server. So it's Dell servers or Lenovo servers or HP servers. And this designed by this because we know that organizations will have legacy equipment. And we want to enable them to run that legacy equipment more efficiently and connect it with our systems, for instance, to enable them to scale out and grow their data storage. Or if not, they can run it just uniquely on their own, on servers and equipment that they've set up. And the software solves so many of the problems. Remember I told you about the the data backups of file corruptions or data migrations. Well, the software does that automatically, and it reduces the overhead for managing data. So let me tell you about how it works. Typically, when you have a file management system like ZFS, what you need to do is you need to replicate that data. So you have the original file, which is like 1 petabyte, for instance, and you make 1 backup or 2 backup copies. Now you have 200% overhead just for the backup copies. 2 copies, 200% overhead. That's 3 petabytes of data that you have to manage. And the speed is basically limited to the one system where you've stored the data. So it's one input output. We were thinking, can we reduce that data volume, but increase that resiliency that organizations need so that they can still have the access to the data if servers are failing or disks are failing? And we came up with a solution using erasure coding. So what erasure coding is basically it takes data and fragments it and builds parity scores. But what we've enabled, what's unique about ours is that we can build any data, any parity. And I want to show you how that works. So here we built a network of 9 servers that are connected into one namespace. And anywhere in that namespace, we can ingest data. And a data file comes in, it gets fragmented into data slices, 6 data slices, for instance, and then 3 parity slices, 3 parity fragments. The parity fragments and the data chunks are then stored on the network in a random fashion, well, random in particular, but that allows us to then get high resiliency. So for instance, if you have a disk failure or node failure, or even a file corruption or bit rot, the system is able to rebuild the data on the fly on the missing chunks and the available chunks and send it back to the end user. The end user never even knows that there's some failure occurring. I'm going to show you a little video just to demonstrate how that works and how it's really fast as well. So if it's in the same data center on the same network, it'll be very quick. It'll be very fast in terms of data sending back to the customer. But if you have distributed across a large network, there might be some latency. But basically, it's ideal for long-term storage or even this sort of fast processing where you need to feed GPUs in this parallel management. So basically, rather than reading from one drive or one server, you're reading from multiple servers in a parallel fashion. So, and the other advantage is that rather than having 200% overhead that you have to manage just for that one data file, with this 8 data 4 parity configuration, you reduce that data volume by 50%. So we only have a 50% overhead. If you wanted to set it to 100 data and 5 parity, you're down to like 5% overheads. But the beauty is also in the fact that in the top example where you replicate the data, you have 2 backup copies that can be corrupted. Once you lose these 2, your data is at risk. On the bottom, you can lose up to 4 data chunks or parity chunks, and you're still fine. You can lose 4 servers or 4 disks if they're distributed highly, and you get high resiliency for the data. Okay, so I'm going to show you a little video of how this works. So what you see here are 20 disks in the vertical green bars. These vertical green bars are, as I said, 20 disks, and what we're going to do is we're going to have the video that you see that's playing on the left-hand side, bottom, is going to be fragmented into 10 data chunks and 10 parity chunks. That means that we can tolerate 10 disk failures before you lose your data access. And so remember, it's not replicated across them. So whenever time a disk is removed here, which simulates the failure of that disk, the system is saying, I'm missing data chunks, I need to repair this. And it does so on the fly. And so the end user never even knows that systems are failing. We've demonstrated this multiple times in multiple organizations that are trying this. And now you see that 10 disks have been removed. The individual here is gonna replace some of the disks, which is also important because when systems come back online, you want to get them to be integrated automatically back into the file system. And so that in case other systems fail, and this is the resiliency that's built in. And now he's removing additional disks. So 15 disks will be removed, and the video kept playing all in real time. So this is important for content delivery, feeding GPUs, etc. The systems never go down, basically. Okay, and the other advantage is that when you have, as I mentioned, this is just shown graphically, if you have 10 petabytes of raw data, you build 2 backup copies. You have 30 petabytes that you have to manage. But by using erasure coding with 8 data for parity, you've now reduced that by 50%. So now 50% of your volume is free to store more data. You can store more data in your data center and increase the resiliency by a factor of 2. Because on the top, you can lose up to only 2 servers. In the bottom, you can lose any 4 servers before your data is at risk. So that's a dramatic cost savings and allowing you to store more data in less space with less energy and less infrastructure. This is another important point, is that often now, as data is growing, people are using databases that are now very far apart. And we want to be able to increase the speeds of the utility of that data. So here we had access to Lumen's network. They gave us access to 4 data centers in Seattle, Phoenix, New York, and London. We had access to a server with multiple disks. We fragmented data and stored it across this network. And what we were able to show is that because we do it in high parallel mode, in this case 10 data chunks, we were able to speed up the network from the targeted 15 megabytes per second that's expected to 150 megabytes per second that we achieved by the data transmission speed. So that shows you that even if you have a large network, a geo-distributed network, we can increase the speeds dramatically. And that's also shown here as well. So one of the advantages of Vault file system for GPUs and machine learning is that we can increase the speeds so there's not waiting for data feeds. If ZFS is the common data storage file system, and if you're using Vault file system, you can see with over like 5 different nodes, the speed up is 5 times faster than in the write mode, and it's even 7 times faster that we measured in the read mode. So we are much faster because of the massive parallelization that we're able to generate. If you did 100 data chunks and 100 servers, your speed will grow linearly to about 100 times that rate. And the other advantage, remember, a Vault file system is used in current data centers on the equipment that they have. As long as it has vector acceleration, we can use any type of server, so there are no hardware accelerators are required. And this is important because systems will grow, they'll scale, and we need to be able to connect heterogeneous equipment. And in any case, we can also connect any data disk as well, any volume of size. So if you have a data disk that's 5 terabytes, now you added 15 terabyte disks. Typically in RAID, you can only use 5 terabytes in both disks because you're set with volume. But here, what we can do is use the full data volume from these heterogeneous disks and connect heterogeneous servers as well. And this is an important aspect of being able to enable data center managers or data managers to grow their network. And finally, one of the things that we have removed from the equation is that we reduced the risk of ever losing your data because it's highly distributed. So systems failing, they're fixed on the fly. If your data is the disk is failed, the data is rewritten somewhere else in free space in the network. If your server fails, the disk can be redistributed in the network. So by this equation, by this fact, we remove the equation from the equation, the loss of your data, the probability of loss of your data. So now you can run your systems to the end of their life. And so this maximizes the CapEx investment for most data centers and reduces their electronic waste. Okay, so I'm coming to the end of the presentation, so we can leave a lot of time for Q&A. And so what I presented to you is basically the data storage hardware for high density, low energy efficient long-term storage. So that's a unique, innovative design. And we also presented the Vault file system, which is using erasure coding and enables data center managers to build a robust and resilient long-term storage solution. And so by combining the two, or even using one or the other, we've simplified the data management headaches, and we enable high performance speeds, and we enable to reduce the energy consumption and also the electronic waste, and also construction of data centers to make data more sustainable. Okay, thank you very much. So I reached the end of the presentation. So we have, I turn it over to Dan to run the Q&A.
Yeah, that was fantastic. Here, you go ahead and we can drop your screen share for a minute there. And if anybody
Sure.
has any questions, this is the time. I'll say that, look, you're able to build a data pipeline at a high speed with old hardware. I mean, that's phenomenal. And also the integrity of that. Imagine trying to run a big job and train a model or do some other fine tuning on data sets or discover new information. And then you get bad data because there's corruption, okay, or something. You're spending money to do something and you're getting bad information or incomplete data because of some failure or another. Or here you're able to create a pipeline where you weren't able to before with cold storage, long-term data. I have my friend worked on the Human Genome Project, okay, as a programmer, and there's a lot of data back then that was being used for this, and that's here at the UW, University of Washington here in Seattle. But there are so many, companies and other universities out there doing research where, wow, we could wake up this data and do something with it, or even on the other end of things, we could make it available where it normally wouldn't be, in some cases, and so I've seen so many cases where a small form factor solution like SwissVault provides would be the game changer. It would be what makes it happen, what makes the project even possible in some cases, because space is an issue. Power consumption is a huge issue, and not all these different locations, exactly have like the best resources depending on where you're at. And the ones that do have so much data that, what in a few years, it could double for some people. And so that's a factor. I see we've got a question from Patrick here.
Good. Hello.
Hi there.
Can you hear me all right?
Yes.
Yeah.
Good. I had a few questions. So what are the interfaces to get data in and out of this thing? Does it do 10G? Does it do multiple 10Gs? Does it do fiber channel? Is it a NAS? I mean, I get storage, but how do we do it?
So I can answer that question. Basically, anything that Linux can handle. So we do run it over 10G. 10G tends to bottleneck the system. It's quite efficient software, so it would like 25 or 40 or 100, but 25 is usually good. And we do run it on InfiniBand at both 40 and 56. G. So pretty much anything, if Linux can communicate via it, it's agnostic to how it comes in. I see. There's another question there. How are we different from RAID, there's two different things. The first thing is the number of parity. So RAID typically is either 1 or 2 parity. So we're just talking about RAID 5 or RAID 6 because we like to stay away from the other methods because they duplicate data and, you know, double or triple the cost of the hardware. So RAID 5 or RAID 6 has 1 or 2 parity, and VaultFS has any parity that you want. So you want 5 parity, great. You want 23 parity, that's great. And the other difference is RAID always works on one server. So if your disks in your one server fail, then RAID can handle it. But if your server fails, then it's gone. Whereas VaultFS distributes all the data and parity chunks over different servers so that we can even tolerate not only disk failure, but also server failure and network failure as well.
All right. We have a question here. Let's see, from David. How can a potential user roughly estimate the amount of energy that they will be saving and the amount of emissions that they will be canceling as they calculate migration to SwissVault? That's a great question.
I'll answer that question
Right.
because people say, well, how can software possibly reduce energy? And the reason is because we can have any data with any parity mix, we can vary the overhead. So if we have something like 10 data plus 5 parity, that overhead is 50%, which is quite high. And RAID can do a little bit better than that. But when we go to 50 data plus 5 parity, first of all, the parity is increased and your safety is increased. But look, the overhead has gone down to only 10%. So that is how you save the energy and also capital cost as well as running costs. So because we, with our own proprietary erasure coding, can vary the ratio between data and parity, we can control the overhead, and that's how you save money. So
Right.
if you want your overhead to go down to, let's say 3%, you could use 100 data plus 3 parity. So
And
this is incredible.
And so David says, so can you say you are saving as much as 90% of energy required to run a data center?
With the software, that's what I'm saying. If you use 100 data plus 10 parity, then your overhead's only 10%, so your savings about 90%. And this is applicable to large files over, you know, a few megabytes.
Okay.
So not for tiny little files, but for
Right.
big
Right.
laboratory or virtual snapshots or things like that that are usually megabytes or bigger. Yes, I'm saying exactly that. You can use only 10% additional hardware and building space and energy to go in and cooling energy, whatnot. Yes, the savings are there with this
Okay.
flexibility.
Nice. Patrick asked, does it support block storage and does it encrypt data at rest?
And we do not do block storage. It is a POSIX file system. So and store any files, and it's optional to turn encryption on. And if you do that, encryption, it's encrypted at rest and in motion. So we were looking at Filecoin the other day, and that, strangely enough, does not encrypt your data at rest. So you know you've got somebody else storing your data, but it's not encrypted. You know you don't want that. So you can turn encryption on, and not only that, but we can layer encryptions with up to 256 different ones. So type A and type B and type C, and you can give us your executable for your own proprietary encryption, and we can use that or any of the standard ones. So just huge encryption
Uh-huh.
possibilities.
Right. And I worked with file systems for many years and for lots of different purposes and had to hack a lot of things and do things with security. You guys got where you are now through security and encryption. And I think it's worth mentioning that this is something that you know very well from the ground up. I think it's worth mentioning that the streaming capability from your arrays is much like a block cipher, just like you would use in encrypted tunnels and things like that. But anyways,
That's completely true, because the erasure coding essentially scrambles the data for the parity. And when we encrypt both the data and the parity. And the other interesting thing about data plus parity is that you only need the number of data pieces there. So if it's 10 plus 5, then you just need 10 pieces. And they're all sent in parallel, and you can use the first 10 pieces that arrive to decrypt and get your data. And if there are some slower channels, then those are ignored, because you've got the first 10 that you need. And that decreases the latency, like Bhupinder was saying before. So
right. Nice. And I've got two other questions here. One of them, can you clarify if organizations would then have storage locally instead of the cloud, or would there be various options for where the physical entity would be located?
Okay, so we have not tried storing anything in the cloud. Theoretically, it's possible, but you can have the data locally, or you can have it distributed. So if you've got, say, several branch offices, you can choose to distribute it in several different places. To give you an example, if you've got 3 main storage locations using 10 data plus 5 parity, that is kind of like 5 plus 5 plus 5. So you put 5 chunks in each of 3 locations, and one entire location can burn down. Doesn't matter which one, and you're still good. So yes, we can distribute it, and that's all part of the game. Or it can all be in one place.
All right. And then Robin's got 2 questions here. How would SV technology assist with agricultural sensors and data collection and computation at the edge? That's the first question. So how could SwissVault assist with agricultural
Vault
sensors?
FS is mostly meant for big files, but one of the things that it can do is small files, and you do get the redundancy of transmission, the parallel transmission. So, and typically agricultural data is not that big, so it transfers fast, but it will assist with the transfer of data. So not sure how good it would be for small bits of field data, but it'll definitely work. So you've got the same system out in the field as you do in the data center, and that's always nice to have a homogeneous integrated system.
I'd like to touch on the homogeneous part, because basically what we're looking at, what we're witnessing from a lot of the edge sensor IoT stuff, is that data is captured, sometimes needs to be stored at the edge. But if you have a one seamless system that connects the edge to the data centers, you're able to then enable a seamless homogeneous system that manages your data. And so you can extend it. But at the edge, basically, you might have one storage node, but if that fails, your data's gone. But what we've done is we distribute that data across a wider network, and you can enable highly resilient data at the edge and faster machine learning or AI inference as well.
Wow. And Doug, you're the right person to ask this question, because you're the CTO and inventor of what the technology behind Vault File System. And so you have this incredible knowledge here. And so Robin has another question. If one is interested in testing SwissVault software, how can we accomplish that? And what's the process? Also, how does SwissVault software provide data security?
Okay, so the testing is really simple, because we've got clusters at our facility. So the first, 20-minute commitment is for someone to log in with us into our own system, and we'll show them around. And it's POSIX, so it's the POSIX that you know and love in Unix. And really, the user who's using it doesn't think anything is abnormal. Now, the system administration, he can change things like the erasure coding on a directory or a particular file, or turn different types of features on and off, like encryption and various levels of compression and whatnot. So the quick 20-minute commitment is to log in with our system, and we'll show you on ours. And the next commitment at another time would be about an hour or an hour and a half, where we get permission to remotely log into your cluster, and we'll install it. The installation takes about 5 minutes, not including disk formatting, if disk formatting needs to happen. And disk formatting only takes about 5 or 10 minutes because it's in parallel.
Wow.
So very, very easy to get into demonstrations. And can you remind me the second question?
Okay, that was it. So, so just testing SwissVault's technology. So I put a demo.
Yeah. There's a question about the security because of the erasure coding, and it's sent all over the place, and it can be encrypted. Then you've got the security that you want. There's also another feature of it is Worm. You can set the administrator can set write once, read many times. And it's a rather robust kind of worm where even the system administrator who has root privileges cannot delete a file. So even sysadmins make mistakes. There's an example of someone who deleted all the backups in the Japanese Fugatsu computer because he was the root, and he just made a mistake and he deleted the wrong directory. Well, we've got sort of procedure in place where if you do worm, you've got to be very specific about who can actually delete it. So it is secure that way.
Patrick has another question about vector store run on this kind of storage.
Right. So will a vector store run on this kind of storage? And
I'm unaware of what vector store is. What is vector store?
It's an embedded sort of database on top of your file system. Whatever
well, if you can,
would run on top of VFS, from what I know. So
I'm without knowing what vector store is, I'm going to say probably, because and why can I say that? Basically, any file that you can write to normal Linux in XFS file system or whatever, then you can write to our VaultFS file system. And this includes, getting all the A times and soft links and hard links and all kinds of other things. A more complicated example would be that Fraunhofer's BGFS, as well as Lustre, don't have any internal parity correction. So they are run on top of ZFS. And so those are quite complicated distributed file systems, but those both run on VaultFS, so that you can run those to get our erasure coding and higher parity than you can by running those components on individual RAID controllers.
okay.
So I'm going to say if you can put a file onto a normal Linux file system, then it can do it. The caveat is it's meant basically for long-term active archive storage and not for databases. Something with high transactional content. It's more for storage and retrieval rather than transactional. That's the only caveat.
Okay. So Deepak asks, what is the recommendation for file data size to get effective storage savings? We have a large Hadoop system with many small files, and when we tested the HDFS erasure coding on small files, savings were not impressive.
Okay, so it depends what small means,
Okay.
and
Yeah.
if
All right.
small means 120 bytes, then one way. So these big parallel file systems, they basically don't like small files, but we can do it, and we can store 0 byte files even too. And some systems have sort of little accounting 0 byte files that they use to keep track of processes and whatnot. But one way that we can handle that is and this is used quite a bit in virtual data backup. So there's many files that are coalesced into a big file. So if you can put a file into zip or ISO or tar file or something like that, then you can basically take advantage of the better compression of bigger files.
Mhm.
So if you do that, you can actually use the Unix utilities or the zip utilities to pull out files from within the middle of that file. So let's say you've got 1,000,000 100 byte files. So you pack them all together, stuff them in VaultFS, and then either the system utilities that are already there, Unix utilities, can pull the middle of the data out, or we've got other read-write options. We call it magic files. So we can pretend that a zip file or an ISO file or a tar file is a directory, so that your program that doesn't know anything about zip files or tar files can pretend that that's a directory and go into it and pull it out, even if it's compressed. So
Mhm.
yes, you'll be quite amazed at what we can do with small files.
Mhm. Nice. That's a good way of doing it. Let's see here. It looks like Bhupinder is typing an answer out here for us. That's a good question. Let's see here. I'm just going to read it. So I'm a researcher focused on business continuity management. Oh, it's been answered. Okay, good. Okay, you guys.
I can
It's a good
answer basically
question,
that
though.
one.
All right.
The answer question was about affordability for small and medium
Mhm.
enterprises.
Right.
And at the moment, on our first release, we're really targeting on the major headaches that are associated with petabyte scale management.
Mhm. Right.
And so I mean, we do have a couple of projects going in different regions where it might be smaller amounts of data,
Mhm.
but largely this is the solution. So if you are interested in using it, come talk to us, and we'll try to see if it's the right solution for you at this time, or we can suggest a more affordable, or even not affordable, but more efficient solution for your organization and your needs. As I mentioned, once you get to petabyte scale data, you have a lot of headaches and just manage the data. So this is what
Mhm.
we want to solve.
Right. My friend does video editing for movies, and he has a 40 terabyte NAS storage unit at home, and it's getting full, So
Yeah.
there's a lot of places. I mean, I like the question about for small, mid-sized businesses, because there are, video editing firms that might be able to take advantage of something like this. There's a lot of people out there in the medium end of things that work with, im- inconvenient data. All right. You're trying to move very large files and then edit those files. I mean, yeah, video editing is
When you're
something
a
else.
creator
And,
like you are,
and
Dan, I mean,
Yeah.
this is a very important stuff you're creating, and you don't want to lose it. So we want to be able to enable, if systems are failing, disks are failing,
Mhm.
or servers are failing, your data should be protected. And that's
Mhm.
And
what we
it's
want to do.
amazing how our perception is changing. So you mentioned 40 terabyte file systems overflowing, and we've got systems where you can put that in the palm of your hand.
Mhm.
So
Mhm.
for us, pretty soon, it's not 40 terabytes that is the limit. It's like 100, 200, 400 is like, yeah, just another day at the office.
Yeah.
No big deal.
Right. I mean, I remember when a gigabyte was $1 on a hard drive, and that was where we were at in the early 2000s at some point, and now here we are with, really great high-end M2 memory and more, and
Well, it's quite amazing because Seagate now has the 20 terabyte drives, and the 30s are coming out this summer. If you think of it, that's a 50% increase in capacity in one jump.
Yeah, it's a huge deal. So I used to work with a lot of RAID systems, and it was usually small, but some that were corporate wide, and it's necessary, and it's necessary for so many things in one business to have. And then the whole idea of creating it as a utility as well, and having this a little bit more widespread is wonderful. Especially with all the exciting things that I've been involved in at this organization in California, and it's global. It's called Quai, and it's a nonprofit. But we all have some great opportunities in front of ourselves right now to build things new, and to approach things in a more sustainable way, and that makes things possible. I mean, not all budgets are going to fit a standard deployment of something, but if you can make this footprint smaller, this energy consumption smaller, a project is now suddenly more green, and it gets accepted and gets funding because of that. I mean, this checks a lot of boxes for a lot of big reasons. And, I, again, have been excited this whole time about where you guys have been taking things since the first time you were on. So, it blew my mind. I thought to myself, that's just a huge percentage of gain there. And also with the resiliency, it's super important. And again, you guys got my attention because I figured out in the conversation that it must be a block cipher they're using or something, and it's streaming so quickly. And then when I saw the video with the hard drives, I thought, yep, okay, all right, this is great. And that's why I say, you could approach this as a pipeline. You can ingest data slowly. It doesn't have to be in real time. You can feed off of cold storage and re-ingest that in a different way, and vectorize that and store that in a very light database easily.
Yeah. Can I just throw something in? So if somebody doesn't have block storage, if they've just got a bunch of storage, let's say a legacy system that's 3 years old, and they're thinking about retiring it, and they've got a bunch of data on there, VaultFS can actually co-reside with other data on formatted disks and sort of absorb it while it's reading that data, and just from one disk, it can be erasure coding it and distributing it over many disks. And at the end of the procedure, everything is now erasure coded and distributed. But, if you've got 2 petabytes, you don't have to have another 2 petabytes to put your data and then put this new one in. It especially is applicable to older systems. And as Bhupinder said, run the equipment to the end of its life. So this is applicable to someone who's at a 3 or 4 year cycle. And we're saying, okay, let's just migrate instead of like a forklift upgrade where, the budgeting, is a multi-year budgeting, and suck in your breath at the bulk cost that all happens at one time. You can do it incrementally, and on from the same storage to the same storage, without any great upset, and like almost zero cost, hardware costs.
Yeah, that's really slick, where you don't need another backup set of disks to back up to completely. That's wonderful.
And then we like to
I needed
announce
that 20 years ago a few times. So definitely. What's that?
we'd like to announce that, if there are universities out there that of, the research centers, that we're willing to let them, we're basically opening up for them to use it for free. And so if anyone knows any university or research center, please contact us. And so we're also doing it with the New Jersey Big Data Alliance, and we've been with the University of Binghamton. Tremendous effort there on their part to test and validate some of the things that we presented today. And all
Right.
the research, the performance data was also coming from some of the work that they did as well, that you saw presented here.
Right. That's amazing. Yeah. And we have,
People can,
yeah.
they can contact us directly via you or just directly to me
Mhm.
if you need
Yeah.
any questions. So
I'll put your emails in here again for people who came later in the show. Here, let me get that, and we'll go ahead and put that in the chat for everyone. Here we go. Make that easy. There we are. And then again, I'll get the request a demo link for everyone and put that in to the chat. There we go. Excellent. Yeah. Okay. Here we are.
great.
Yeah, it's been fantastic to just get to see everything over again and look at it and go, wow, I wasn't hallucinating. It really was a 30% savings in some cases, with just the size. And I know that was and especially because I'm thinking about big data. I'm thinking about long-term, let's wake up that data, let's use it, let's find trends and things that we missed. Let's utilize it because it's gold. And people are sitting on gold they don't even know about because it's inaccessible or it's inconvenient. And there's a lot of reasons. Again, I think that we'll find all kind of ecologies crop up around this technology where all of a sudden it's making things possible in ways that normally wouldn't be. And again, the whole edge and small form factor approach and doing things like that, I feel like it's the future. It's right now. Even we need that. So yeah, and it's not just and people out there to understand this isn't just SwissVault. Other people are agreeing that this is a great way to go, and SwissVault has the answer for that, and that's what I'm so excited for. I'm really glad that you guys chose to be involved in my efforts to democratize AI through Quai, and to actually be a part of that community because we are all building this together, and it's huge and it's multinational. This is everywhere. Um, and I haven't seen anyone do this much. SwissVault's done it, and it's incredible. So I have to thank you both for coming out and taking the time with us today
Yeah.
on the show. Yeah, I'm Dan Wilson, and this is the AI Think Tank podcast. And for anybody out there that has further questions, you can always email us. And again, we have contact in the chat for everyone here. And so I urge you to go and request a demo and see what this is about for yourself, and just see the performance because it's legitimate and it's powerful. So again, thank you both for coming out. This is the AI Think Tank
Thank you, Dan.
podcast. Have a wonderful
Thank,
Saturday, and we'll be talking to you soon. Okay.
thank you, Dan,
Thanks
for
so
your
much.
All right.
yeah.
Thank you. Bye, everybody.